Welcome to Maths with EJD. I'm still talking about numerical optimization techniques. And we've been in the last two videos, I've been talking about derivative free methods. That is methods that do not require you to differentiate a function to get a gradient. So, I mean, before now, we've talked about gradient-based methods like conjugate gradient, gradient descent, and Newton method. But under derivative-free methods, we've talked about the Nelder-Mead method. We've talked about the genetic genetic algorithms, which is based. Nelder-Mead method is based on some kind of geometry, and then we have genetic algorithms based on biology, things like mutation, crossover, and selection, and then we are going to look at simulated annealing in this situation, simulated annealing, which is based on the cooling process in metallurgy. So, um, we have considered Nelder-Mead method in a previous video. Then we've seen genetic algorithms. So our focus now is going to simulated annealing. Simulated annealing. So annealing is a metallurgical thing, like I said already. And we see that simulated annealing, or SA for short, is a probabilistic, optimization algorithm. So it is based on probability. So a probabilistic optimization algorithm inspired by the process of annealing in metallurgy, where a material is heated and then slowly cooled, to reach its lowest energy state. To reach its lowest energy state. Okay. So the algorithm attempts to find the global minimum, of a function by exploring the solution space. Balancing exploration and exploitation. Okay, that is the simulated annealing process. Now let's see how that works, how it works. Okay. Of course, as usual, in most situations, we talk about an initialization where we start with an initial solution, or what we call initial guess in some situations. Starts with an initial solution. So the algorithm starts with an initial guess for the solution. This could be a random point in the search space or an informed starting point. Okay. The second thing that happens is you evaluate the solution as usual. So you have starting solution. So you evaluate the solution at that point. So the objective function, which is, for example, the cost or energy function, is evaluated at the current solution. That's that step. Then point three, you generate neighboring solutions. Generate neighboring solutions. So a neighboring solution is generated by making a small random change to the current solution. Say you have two as solution now. So you may want to check for maybe 1.9 or 2.1 or things like that. So something value is very close like that. Then in step four, you have to evaluate the acceptance. You have to get the acceptance criteria. Acceptance criteria. So the first one is if the neighboring solution is better, that is, it gives a lower cost or lower energy, then it is accepted. Okay. Then the second one is if the neighboring solution is worse, it might still be accepted with a certain probability, which decreases over time. This probability is typically determined by a temperature parameter T. Since we are talking about cooling, right? So we have a temperature parameter that gradually decreases according to a cooling schedule. So the probability of accepting a worse solution is given by the formula. So let's see that. So the probability of accepting a worse solution is given by this formula here. So probability that you accept a worse solution is E raised to power minus change in energy over T. So where delta E is the change in energy, and T is the temperature parameter. The temperature parameter. Okay. So we have this now. Now we have ideas relating to cooling schedule and all that. Okay, I guess that should be the fifth step in the process. Number five, we have a cooling schedule. Cooling, the schedule or schedule, one of the two. The temperature T is updated over time, usually by cooling it according to a schedule. So the schedule could be something like T could be equal to alpha T. All right. So, and alpha would be a constant. It's a constant less than one. Okay. That could be the cooling schedule, depending on what you choose. So as the temperature decreases, the algorithm becomes less likely to accept worse solutions, focusing more on refinement rather than exploration. So that's talking about the cooling schedule. And finally, number six, we should have a stopping criteria, just like for every numerical solution. So we have a stopping criteria. Okay. So the process stops when a predefined stopping condition is met, such as reaching the maximum number of iterations or when the temperature has sufficiently decreased. So these are classic stopping criteria. Like if you just maybe you want to just do 5 iterations and you stop, or you want to stop when the the value of what you're evaluating is getting close, they are really close and there's barely any remarkable change. All right. So having said all of this, can we go on and talk about let's go on and talk about some example that can drive the point right home. So let's go for that. So example, interest here, I'm going to have like two examples. So let me do one straightforward example and the other one will be like some kind of optimization issue. So consider the objective function. Consider the objective function f of x equals x squared minus 4x plus 4. Don't forget, we are considering derivative-free methods. And most of the times, the examples we solve are very simple example that you can actually solve using gradient-based methods. But they are very simple, so we can easily demonstrate the process. So you can use the idea to apply it to more difficult situations, okay? So consider the objective function f of x equals x squared minus 4x plus 4. So we want to minimize this. So find the minimum, find the minimum of f of x. Basically, that's what we are interested in. So we go step by step with the solution. So we have one, initialization. So you can start at x equals 0 and the initial temperature. We are annealing is a temperature thing, so don't forget initial temperature T naught equals 100. So we have that, right? So then we also take the cooling rate. The cooling rate alpha is 0.95. So with that, we take care of initialization is taken care of like that. So the next thing we want to do is that's step one, right? The step two now, you evaluate initial solution. Evaluate initial solution. That's the next thing we do with the first set of parameters we have. First set of parameter values, so to speak. So here we have f of, we start with x equals 0. So f of 0 is 0 squared minus 4 into 0 plus 4. And that is simply 4, right? So next we want to generate okay, I mean that could as easily pass for step 3. So let me just take it as step 3. So generate neighboring solutions. Neighboring solutions. So so you can just say randomly choose a neighboring point, say x equals 0.5, which is close to 0, by the way. So that's the first thing we do there. So randomly choose a neighboring point, then evaluating neighboring solution. Okay, we have f of 0.5 equals 0.5 squared minus 4 into 0.5 plus 4, and that is equal to 3.25. Knowing that 0.5 squared is 0.25, then this is 2. 2 plus minus 2 plus 4 is 2. So 2 plus minus 4 times 0.5 is 2. So 4 minus 2 is 2. Then 2 plus 0.25 should be 2.25, right? I think it should be 2.25, yeah? So this is 2.25. Hope that's correct. This is 0.5 squared. That's 5 times 25 to decimal place, 0.25. Then plus 4, that's 4.25. 4 times 0.5 is 2. So 4.25 minus 2 is 2.25. Okay, so that goes. So the next thing we want to do is to accept worse solutions. So accepting. So what are the steps again? Let me see what the steps are. So evaluate solution, generate neighboring solutions. So this is more like step 4, actually. This is like step 4. So 5 now. Step 5. accepting worse solutions. So you can see what we got with 0 was 4. But I mean, with 0.59, it's 2.25, which is smaller. So we say accepting worse solutions if the neighboring solution had been worse. So we see the neighboring solution is better. If the neighboring solution had been worse, say x is equal to -1, we calculate the probability of accepting it. Which would be f of -1 Okay, I mean, we don't need this, right? So we already have the result, how to calculate probability. So probability of acceptance, probability you accept is e raised power minus change in energy all over um t, which we already have. So this is like e raised power minus change in energy. So of course the energy would have changed since the decrease rate is 5%. So the energy would have changed by 5 over 100. So we have e raised power minus 0.05, and that is equal to approximately 0.951. Okay. And then we go for cooling now, like step 6 or so, cooling. So we see that after each iteration, we decrease the temperature by multiplying it by alpha equals 0.95. That's the rate of cooling or something. So the new temperature is T equals 100 times 0.95, and that is the new temperature is now 95 right there. So we can call that T1, right? So we now repeat that step. The next step, should I call it 7? 7 in this case. So repeat. Okay. That's what happens at the end of the day. So the process continues with new neighboring solutions, and the temperature decreasing, and the temperature decreasing over time until the stopping criteria are met, And the stopping criteria could be maybe number of iterations or any other position. To complete this one, I have another example. Like I said, I have 2 examples in this case. So here, now this is the first part, which is talking about this objective function, which we want to minimize. So let me create. So we want to minimize this, and x squared. So this is just like f of x equals x raised to power 2 minus 4x plus 4. So make that into markdown. I'll probably just do this. Yeah, so this is what we are doing here. Yeah, that's what we are doing with this first one. So you have all the So the function is defined and you go through all the simulated annealing procedure, which can be a bit tedious. Now, you can see the problem itself is very simple. So I can just differentiate it. I get 2x minus 4, and I see that the minimum or maximum points there will just be 2 in short, right? But then this is just to demonstrate this. We are just using the simulated annealing thing to demonstrate it. So we have this. So you see, at the end of the day, we expect the result is expected to be 2, and this is 1.9999 something. So and the best value, that's if when you evaluate the function at 2, you get normally you should get something like 0. And this one is really close to 0. That's 0.40 before you get 6412. That's 0.0000, then 6412. So and that this is the diagram that demonstrates that process. So, I mean, we have picked a very simple example that could even be done using gradient method just to demonstrate this. So, if you have functions that can hardly be differentiated, then you can actually apply that there. So, just study this code, which you find on Facebook. Sadly, not on YouTube because of some special characters in the coding that cannot be accepted in YouTube description. So you see that the process is going, the cooling is going, and then it saturates around something like this. So the value is very close to 0. Okay, and then the x value itself is very close to 2, and that is that you have 1.9 something something. And if you look at the function itself, right, one way to find minimum or maximum differentiate, you get 2x minus 4, 2x minus 4, then you equate to 0. So 2x equals 4. So x is equal to 4 over 2, which is 2. So the minimum point is declared to be 2, and this simulated annealing has given us 1.999, which is to 1 decimal, 2 decimal, 3 decimal, 1 decimal place, or 2 decimal place, to but nearest whole number, 1 decimal place, it's still that 2. So that works. And then when you evaluate the function at that point, you get something pretty close to 0. Okay. So let's go for the second example, which is about the traveling salesman problem. Okay. It's a very popular problem in probability. I mean, in optimization rather. So let me switch over to say, look at this and then say this. All right, so that takes us to example 2. Example 2. So we have seen how we can use it for like a polynomial. So let's use it for the traveling salesman problem. So TSP, the traveling, the traveling salesman problem, or TSP, is a classical problem. The classical problem where a salesman, must visit each city. A salesman must visit each city exactly once, that's conserving energy or something. Exactly once, exactly once, and return to the starting point, while minimizing the total distance traveled. Okay, that's the salesman problem. So let's look at the simulated annealing algorithm. So the simulated annealing algorithm for the traveling salesman problem. Okay. Yeah, first thing is initialization, right? Initialization as usual. So this one does not involve numbers and all that. We just need to move around. So we can randomly generate an initial tour, e.g. So you have moved from, you have A, B, C, D. These are the places the salesman has to visit. And then we go for the second point. We evaluate the initial solution. Evaluate the initial solution. So this would involve some kind of geography, right? Because we need to find distance between towns or cities. So we calculate. So what we do is calculate the total distance, the total distance of the tour. Okay. After doing that, then we generate neighboring solutions. Generate neighboring solutions. That means you have to look for alternatives that are really close to what you have. So in that case now, you can randomly swap. So instead of visiting A, B, C, D, so you can just change it somewhere. Randomly swap two cities in the tour, generating a new tour, generating a new tour. Say, instead of A, B, C, D, say you now have A, B, D, C. That's a new way to go. And then you check that out and see if it's a better option, distance wise, for to evaluate. So we have generated neighboring solution. So you now evaluate neighboring solution. Okay. So here, calculate the total distance of the new tour. Okay. So compare ABCD to ABDC. All right. And then that takes us to step 5, where we accept. So you accept the better one. So acceptance now. Accept the new tour. Accept the new tour if its distance, is shorter. You want to minimize distance. If the distance is shorter, but if it's longer, right? If it's longer, accept it. Accept it with a probability probability based on the temperature. Of course, don't forget we are dealing with simulated annealing, which mimics cooling in metallurgy. So based on the temperature and the difference in distance, okay? Then finally, we talk about cooling. Point 6, we have cooling, simulated annealing. So gradually reduce the temperature to focus on refinement. Okay. All right. I mean, since we have not been dealing with specific values here, but let's see what the Python code looks like for simulated annealing for the traveling salesman problem. Let me name it as necessary. So this is traveling salesman problem. Okay. You need to mark down and run. So we have the traveling salesman problem for the second one. So here now we generate the cities randomly. So the cities we added, so you can see it's all randomly. So you see the random library is generated. So we now have defined the distance between city 1 and city 2. So city 1, city 2, the distance between them, you know how to calculate distance in geometry. Now the different distance between x1, y1, and x2, y2 is square root of y2 minus y1 all squared plus x2 minus x1 all squared. That's what is happening right here in line 15. So distance between 2 points on using coordinate geometry. And then in line 18, you have the total distance of the whole journey. So you put all the cities together and see their distance, and then you generate a neighbor, like change the situation, and then you use simulated annealing here, where the cooling thing happens and all of that. So you can study this code that you can easily find on Facebook. If you follow me on Facebook, you can copy it out and just play with the parameters and see how things go. Then of course we want to now define the plot the tour and everything. So I'll just run this. So take time, study the code and see what that looks like. So the best tour here, if we have 7 cities, let me see where specific distances are given. Okay, cooling rate is 0.995, all right. And then the initial temperature is 1000 based on simulated annealing, like that. So since the cities are randomly generated, see what's happening here. In this case, the best distance is 390.74, maybe kilometers or something. So the best twice move from city 7 to 8 to 5 to 6 to 3 to 4 to 1 to 2 to 9 to 0, and then go back to 7. That's basically the thing here. So you see, okay, maybe I should have labeled this better. So but look at what is happening here. So you start from, this is the x coordinate, this is the y coordinate. So start from city, I guess this is the starting point. So 7, okay, this is 7 to 8. This is 7. Okay, I mean, since I didn't label it, I should have done the labeling better. Maybe before I put it on Facebook, I'll try to label the cities. So we see the best path. In short, it is moving from city 7 and back to 0. Okay, back to 0. Yeah. So we have it going that way. So should I think this is 7, 8, 5, 6, 3, 4, 1, 2, 9, and then back to 0. That's what it looks like to me. Okay. So that's what this gives. So we can do better to label the city so we can see exactly how the cities are going. But of course, this is random, right? So if I run it again, it's going to generate something else. So you can see in this case now, the pattern is different. So we have 2, 4, 3. So for this particular process, it's 243 now, and then we have 0, 1, 2, 0, 1, 4, 9, 7, 2. So simulated analytic can simply do this. So if you want something more serious, you can always refine the code to do the job. All right. So that's how it's been this time around. So simulated annealing can be quite an interesting procedure. Mimicking cooling in metallurgy. Let's see if I can get practice questions for us. Okay, before I even go to that, let's talk about summary. Can we just summarize? Okay. So first of all, now the first example, right? It's too simple for simulated annealing because we can do it using other methods. So simulated annealing, SA for short, is effective for large, it's effective for large optimization problems. So it is good for large optimization problems. I think it's more appropriate for that city traveling salesman thing, even more than the first function. But I just use that to explain. Simulated analysis is effective for large optimization problems with many local minima, because it allows occasional occasional uphill moves, uphill moves to escape local optima. Okay. Another point is that it is a probabilistic algorithm, meaning it does not guarantee it does not guarantee finding. So you can see as each time I run the code, you get a different result. It does not guarantee finding the global minimum, but has a high chance but has a high chance, especially with proper tuning, So you have to tune the cooling schedule with proper tuning of the cooling schedule, right? So yeah, so that's how it is. Let's see if we can get practice questions. Okay. Um, so let me just drop one. Let me just drop this one here. Practice. Given f of x equals x squared minus 6x plus 9. Now this is pretty simple, like I said the other time. It's really simple. So we don't have to use this, but I mean, this is the best we can. I mean, just to demonstrate, right? Given f of x equals x squared minus 6x plus 9, apply one iteration, of simulated annealing, starting at x equals 2 with t equals 50 and a neighboring solution and a neighboring solution x equals 3. So you compute the probability of acceptance if f of 3 is greater than f of 2. Okay, that's the idea with simulated annealing right there. So don't forget, you can use Python or any other programming language to find this out. Another one you may want to try, which I will not write, is apply simulated annealing to solve a traveling salesman problem (TSP) with 4 cities, given their distances in a matrix form. So you can generate the cities randomly, and you can take that as a kind of mini project. In fact, I think I should write this. I mean, that will really help. That should help a lot. So let me just go for that too. So you generate the distances yourself. You can even get real distances, or in your city or in your area, and do that. So apply simulated annealing to solve a traveling salesman problem TSP with 4 cities. So you can choose cities around you given their distances in a matrix form. Okay. So I mean, maybe I can even try to generate, let's say, city A, B, C, D, and city A, B, C, D. Okay. So city A from city A, of course, we don't have to worry about that. City A from B is, say, let's say 50 kilometers. That's just me making things up. So this 50 kilometers, of course, B to A is also 50. Let's take it that way. A to C, let's say that's 70, and C to A is also 70. A to D is 82. So this is 82 here. Then B to B, no necessary. B to C now is let's say 42. C to B is 42. Then B to D, let's say that's 27. So D to B also is 27. B to B is also 27. We can do it that way. Then C to C, we don't care. C to C to D, let's say that's I don't know, let's say 37. Why am I saying 7 all the time? So let's say 33. So D to C is also 33. Then D to D is also this. So, I mean, if you have this, can you use the simulated annealing method to solve the traveling salesman problem for these 4 cities? Okay. So feel free to put your answer in the comment section, either on YouTube or Facebook. But of course, you can get the code on Facebook. And I mean, it's coding will be useful for this. The coding is better for this. So you can use the code and just adjust with this now. All right. And of course, let me also know in the comments if how helpful these videos are for you. Let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then if you have subscribed, thank you. If you have not, please go ahead and do that and hit the notification bell so you can always get alerted each time a new video is released. After now, we're talking about constrained optimization problems, talking about things like Lagrange multiplier and the rest of them. So you don't want to miss any of that for sure. So of course, like and share so that more people can have access to this great learning. Till I come your way again, keep doing maths right. Bye.